Okay, this is a worked example for a forces problem, basically covering normal reaction and friction. Package on a rough plane, pretty typical kind of problem. Let's have a look. Package of mass 4 kilograms lies on a rough plane inclined at 30 degrees to the horizontal. As we can see, the package is held in equilibrium by a force of magnitude 45 newtons acting at an angle of 50 degrees to the plane. The force is acting in a vertical plane through a line of greatest slope of the plane. That basically means it's not pushing slightly away or towards you. It's just kind of in the plane of the paper, if you like. The package is modeled as a particle, and that just means that it's a simplification. Basically means everything is acting from the center, essentially. Or actually particle means it's kind of infinitesimally small. Find the magnitude of the normal reaction of the plane on the package. Okay, that's the first part of the question. It's not the first thing we need to do, though, is we need to draw our forces diagram, which means our own clear diagram. Don't be tempted to scrawl on this this diagram that's given with the question. Draw your own, probably bigger diagram, and include all the forces on it. Now, not only do we want all the forces, we want the forces resolved along the two planes in question, which is along the plane and perpendicular to the plane. Okay, I think I would also say normally with these diagrams, we leave the units off because the units effectively are implied by their position on the diagram, either at the end of an arrow or the end of a double arrow, which I haven't got here because there's no acceleration, or within a box, which would be a mass. Not quite got there with this one because I've copied it across. I've cheated and copied it across from this diagram, but that would be the basic idea. So let's populate it with the forces then. We've got this 45 degrees here. I would just say it's an equilibrium on the point of moving up the plane, by the way. So, well, we'll come back to that in a minute because that's relevant for friction. But just taking the 45 on its own, then it is acting partly up the plane and partly perpendicular to the plane, isn't it? And since this angle is 50 degrees, then the component of that 45 acting up the plane is 45 cos 50, and the component that is perpendicular is this 45 sine 50 coming down here. Now I've also got this, the mass is 4 kilograms, so that would imply a weight which would act in a vertically down direction. That would be a weight of force of 4g, but we want that split into two parts, one perpendicular and one down the plane. So since this is the angle between the vertical and this perpendicular to the plane is 30 degrees, then this force would be 4g cos 30, and this would be 4g sine 30. Okay, so that is that. Note here on my diagram, you maybe not quite so easy when you're doing this in an exam, but I've left the original force here in 45 newtons in black, and the forces that I'm interested that are resolved, and also the additional forces that aren't kind of explicit, I have put in green, so it does kind of help to identify the forces that you're interested in for calculation purposes. Now, what else have we got? Well, we have a reaction force here. A reaction force is always perpendicular to this surface. It's effectively the force of the surface pushing up on the particle. And since since these are in balance, then we have no acceleration perpendicular to the plane, then these forces must be in balance. Now, equally, we have a balancing force down the plane because there is no acceleration down the plane either. And the force that keeps that in balance is the friction. Now we know, because it says the package is in equilibrium on the point of moving up the plane, that friction must therefore be acting down the plane, because that's the balancing force. And if this 45 were to increase to 46, then we would actually have a net force up the plane. Okay, so that is friction acting down the plane there. Now we'll come back to friction in a moment. Let's have a look at part A again, magnitude of the normal reaction of the plane on the package. So that is the size of this force here. Right, okay, so what we're saying therefore is, well, we've got that force acting in that direction, but these two forces acting in the sort of into the plane, and so the normal reaction has got to be equal to the sum of these two here, and that's what we've got there. And if we work that out using a value of G of 9.8 meters per second, we get this value 68.42 newtons to 2 decimal places, and that would be this reaction force here. Okay, so second part, the coefficient of friction between the plane and the package. Well, the coefficient of friction, just as a reminder, is a measure of the kind of relative roughness of the surfaces. You know, ice on ice would be very low. The coefficient of friction goes between 0 and 1, so that would be somewhere near 0. If it was a crate on a carpet, that might be something quite high, nearer to 1. And the effort, the force needed to move it, depends on the coefficient of friction, and also, well, it's the reaction force, so it's the effective weight of it downwards, in a sense. And we've got this nice little equation here, which is the maximum friction is the coefficient of friction times the reaction force. Now, what do we mean by maximum friction? Okay, well, if this is in equilibrium, well, let's say we start off here, and this is relatively small force. The friction is in this case just a balancing force, and we might increase this force, push harder or whatever, and the frictional force would increase to counter it, to balance it, but only to a point. And eventually, if you push hard enough, it's actually going to slip. So how high can this maximum friction go in order to counter the force that's been pushing it up the slope? Well, it can go as far as the maximum friction, and that's the value that we can calculate, and we calculate it using this equation. Okay, so that is that's the equation that we're going to use. Now we know this. We know what this is because the net force along the plane is 0. So in other words, this force is equal to this force minus this force, and that's what we've got here. Put another way, this force plus this force equals that force, if you like. But anyway, so this force, which we actually know at this point in the problem is actually at the maximum, is equal to this force, 45 cos 50, minus this force, 4g sine 30. Okay, so just rearranging that, if we divide both sides by the reaction force, which we've already worked out to be 68.42, then we've got this expression for the coefficient of friction, mu, the Greek letter mu. Is that divided by that? Now this just works out. We're using 9.8 meters per second for G. And so we know all these things on the numerator there, and it comes to 9.32 divided by 68.42 is going to give us 0.136 to 3 decimal places, relatively low coefficient of friction, so it looks like the surface is rough, but not that rough. Or even the particle is rough, but not that rough either. Okay, so that is basically it. It's a sort of fairly typical kind of problem. And hopefully that has been useful. So I'll see you next time.